Hi, my name is Rohan Singh Puna and welcome to my channel. In this video, we will be learning about time complexity of algorithms. So let's start off with why analysis of algorithm. Why do we need analysis of algorithms? Analysis of algorithms. A simple case can be, let's say, we want to travel from city A to a city B. Now to travel from city A to city B, we have multiple options. Either we can go by a flight, we can book a flight and just go from city A to city B. We can either take a train from city A to city B, or either we can take a car or a cab from city A to city B, or a bike or even a cycle, right? Although it might take a really long time, right? So now depending on the availability and feasibility or whichever is convenient to us, we might choose an option, right? Similarly, in computer science, we have multiple algorithms to solve the same problem. For example, if we want to sort an array or sort some numbers, right? We have so many algorithms. Like we have insertion sort, we have selection sort, we have bubble sort, we have heap sort, merge sort, quick sort, radix sort, and so on. I can keep going with even more sorting algorithm names, right? Therefore, algorithms Therefore, algorithm analysis algorithm analysis helps us in determining which of them is efficient. Say in terms of time and space consumed. That is what we are much more interested in, right? Time and space consumed. Don't mind my handwriting, it might be a bit bad, but it might get a bit better as we keep going further, right? So, yeah, so this is why we need an analysis of algorithm, right? Now, let's jump on to a very famous example that you may find in most of the places, right? Let's say, we have two folks, one whose name is Adi, and say one is Manav. Okay, now Adi and Manav are given a problem, and the problem is that they need to find if the given number n is prime or not. Okay, now let's say Adi comes up with its approach. Okay, Adi has an approach he thinks through, and he comes up with an approach that if any number starting with, let's say, 2, 3, 4 up till n minus 1 divides this particular number n, then that number n is not prime. So let's say these numbers are represented by I. Then if I divides n, then n is not prime. Same way, Manav also thinks of an approach, but he thinks that if the numbers starting with 2, 3, 4 and up till root n, if any of these numbers divide n, then n is not a prime number. Let's say here in this case I represents all of these numbers. Then if I divides n, then n is not prime number. It's not prime. Now let us try to compare both of their approaches. And before that, let's say one divide operation, one divide or a division operation takes 1 millisecond. We'll assume that one division operation or one divide operation takes 1 millisecond. Okay, so now let's see if given n is equals to 11, then Adi's approach ideally will take how much time? It will take, he will have to compare the numbers, from 2 till n minus 1, which will be nothing but 9 numbers, right? 9 comparisons or 9 division operations. Therefore, it will take 9 milliseconds. Now, in case of Manav, it will take root 9 minus 1, which is nothing but 3 minus 1, which is nothing but 2 milliseconds. Now, let's, take it further, and let's say if n equals to 101, then Adi's approach will take 99 milliseconds. Same way, Manav's approach will take 101 minus 1, which is approximately 9 milliseconds. Now, if 10 is even larger, let's say 1, 0, 0, 0, 0, 3, 4, 5, and 0 and 3. Let's say 10 to the power 6 plus 3. If n is 10 to the power 6 plus 3, then Adi's approach will approximately take 10 to the power 6 milliseconds. If we try to convert this into seconds, then it would take 10 to the power 3 seconds. If we again try to convert this 10 to the power 3 seconds into minutes, right, it would be 16.66 minutes, which is such a long time. Now, if Manav tries his approach with this for this particular input, then it would take 10 to the power 6 root of 10 to the power 6 minus 1 milliseconds, which will be ideally approximately 10 to the power 3 milliseconds, which is nothing but 1 second. Now let's try to increase the input size even further. Let's say the number given is nothing but 10 to the power 10 plus 19. Then Adi's approach would nearly take 10 to the power 10 milliseconds. If we try to again convert this particular 10 to the power 10 milliseconds into seconds, then it would take us nearly 10 to the power 7 seconds. Now, if we try to convert this seconds into minutes or hours or days, right, it is approximately 115 days. And that's an eternity, to be honest, right? It's a very huge long time, right? Let's see if what, Manav's approach will do in this particular case. Then Manav's approach will be nothing but 10 to the power 10 minus 1, which will be approximately 10 to the power 3 milliseconds. Sorry, 10 to the power 5 milliseconds, right? Which will be around 10 to the power 2 seconds, which is nothing but 100 seconds, approximately. Yeah, approximately it's 100 seconds. On the other side, Adi's approach is going to take approximately 115 days, and that's a very huge difference. So as you can see, a small difference in their technique accounts for such a huge difference in the execution time, right? And this is why writing the correct code is not the only thing. What's also important is how your code actually behaves for such large input sizes and how efficient it is. So that is what is very important, right? Now, let's jump on to a fun fact. Let's jump on to a fun fact. A fun fact. The number of particles in the observable universe is approximately 10 to the power 80. So in the observable universe, which is nothing but from the earth, the whole matter in the whole universe which can be observed, from earth, is around 10 to the power 80 elements. Now, if we put these many elements, let's say, in a hard disk, and now let's say if I ask you to search for an element or search for a particle in that hard disk, then if we try to compare two approaches in this case, let's say one is linear search. If we try to use linear search to find a particle in this particular hard disk, which contains 10 to the power 80 elements, then it would take us 10 to the power 80 operations, which is nothing but it will take years. It will take years to find the particle. On the other side, if we use binary search to find that particle in the hard disk, then it will approximately take 240 operations for us, which is even less than a second, less than 1 second. So hence the goal of analysis of algorithm is the goal of analysis of algorithm is to compare algorithms mainly in terms of running time, but also in terms of other factors as well. It can be, memory, developers efforts, and a lot actually others factors. Example, memory, developers effort, and so on, developers effort, and etc. But mainly we are more considerate about the time, right, the running time of an algorithm. Now what I mean by this running time is that this particular running time is how processing time increases as the size of the problem or the input size increases. And that is what we saw with the prime number problem, that with the increasing value of n, the processing time was increasing in both the algorithms. That is nothing but in both the algorithms, if you guys remember, right, t was directly proportional to, if t is the time, it was directly proportional to n in case of Adi's approach, and t was directly proportional to root n in case of Manav's approach. So this is the reason why comparison of algorithms or analysis of algorithm is more important. And in the next video, we will see how to compare algorithms, and we will also look into asymptotic notations. Which are nothing but big O notation, theta notation, and omega notation. So thank you guys. See you in the next video.